Today we're going to look at fractional exponents and radicals. This is section 4.4 in your Pearson textbook. I'm going to skip over the make connections and partner work here. What I'd like you to do is go and give this a try, fill it in, and see what you can see. Alright, so the rule that we're going to look at today is the powers with rational exponents and a numerator of 1. So I'll give you an example of this. So what we're looking at is something like x to the 1 over 5. Okay, so the numerator is the top of the fraction and it is 1. And we'll see what this rule is. So generally what they say is x to the 1 over n, where n is any whole number that is positive, in our case right now, is equal to the nth root. So notice that the denominator of our fraction becomes the index of our rational, and then the nth root of x, whatever was raised to that power. Okay, so in our case here with x to the 1 over 5, we would get the 5th root of x. Now one more example here. If we had 2x to the 1 over 6, 6 becomes the index, and all of what was raised to the power of 1 over 6 has to go in the radical. So that'll be 2x all to the 6th root. Sorry, one more. If 2x to the 1/6 is written like this, the only thing the 1/6 applies to is the x. So this would be written as, again, the 6th root of x, but our 2 is out front. It wasn't to the 6th root. So just a couple different ways of seeing that. Another rule, the powers with rational exponents rule. If we have x to the m over n, so now our numerator is not 1. We have two ways of writing this. We can say that it is equal to n, again, the bottom of our fraction is the index of our radical, and x is to the m underneath the radical. Okay, so the numerator becomes an exponent, the denominator became our index, and whatever was raised to that power went underneath our radical. The other way of writing this, so it's the exact same thing, but we can write it again 2 different ways. We can say x is to the n, and all of this is to the m. This is just showing different order of operations, which still gives the same rule. So this says that we would raise x to the power of m first, and then take the nth root of it. In this case, we're going to take the nth root of nth root of x first, and then raise that entire number to the power of m. So there's a few different ways that we can look at this, and we'll do some examples to see when it might make the most sense to do either. Okay, there are a ton of examples in this section, so I'm probably just going to do 1 or 2 from each example. And what I'd like you to do is try the rest of them, and you can check your work by looking at our completed PDF notes online. Okay, so I'm going to do D. Okay, so write each radical as an exponent. So what we're doing here is we're going backwards. Don't forget our rule was x to the m over n is equal to, we can say n to the xm, or remember, x to the n all to the power of m. So that's what we're looking at here. M, in our case, is 7. Okay, so we're going to have something, whatever is underneath our radical is our base here. So we're going to have 8x. Now, because there's 2 things here, we need to put a bracket to show that it applies to both the 8 and the x. It's to the 7 over, now we have to identify what the index of our radical was. The index is 3, so it is 7 over 3. Okay. In this case, we're trying to write each exponent as a radical. So we're trying to go backwards. I'm probably going to do C and D in this case, just because they look a little bit different. So C, we have a decimal for our exponent here. So what do we need to do is turn our decimal into a fraction first. So there's a few ways you could do this. This is 2/10 based on its place value. So we can reduce that to, 1/5. You could have also done this in your calculator, or if you just know that 0.2 is 1/5, go for it. Okay, this is 2x to the 1/5. Now, note that the 1/5 does not apply to the 2 because it's not in brackets. So our 2 goes out front of our radical. X is the only thing that the 1/5 applied to, so it goes underneath our radical. X is to the power of 1, so technically you could write this one there if you wanted. But what we'll write is the 5th index there. All right, D has a couple different things going on. There's a few ways we can approach D. So 3x to the power of 3 is all to the power of 2/7. So I can put that underneath. So 3x to the 3, all underneath my root. And then the root is a 7. And I can either write this as a 2 here, or I can write this as 3x cubed to the 7th index, I guess, all squared. The last thing I could have done with this one is I could have dispersed the 2 to the 7th to everybody. Okay, so I could have written this as 3 to the 2/7 times x cubed to the 2/7. Oopsie. So that would have equaled 3 to the 2/7 times x to the 6/7. Now, if I put these into their own little radicals, I could have seen that it was 3 squared all to the 7th root times x to the 6th all to the 7th root. Now, because they're both at the 7th root, I can bring them together. I could also say, first off, that this is 9 times x to the 6th all to the 7th. So bringing them together, remember it's 9 times whatever's underneath that root, so 9x to the 6th all to the 7th root. Here, I probably should have dispersed my 2 as well. So we would have gotten the exact same answer here. 7th root. 3 squared is 9. X cubed squared is x to the 6th. Writing this exponent in 2 ways, I'm going to leave that for you guys to work on. Evaluate the following. Evaluate means simplify as much as possible. Okay, so I'm going to do B and I'm going to do D as well. So B, negative 27, all to the 4/3. So this is a 3, negative 27, and that's a 4. Negative 27, and that is all to the 4th root. Now, when I wrote it like this, what I have to do to solve this is I need to apply negative 27 all to the power of 4. If I wasn't using a calculator here, that would be really tricky. So what I'm going to do is I'm actually going to write this in the opposite way. So what we can do is we could say that this is negative 27 all cubed. And then after I do that, I will raise it to the power of 4. The reason being, when I cube root this, it's going to get smaller and a more manageable number that then I can go and raise to the power of 4. So the cube root of negative 27 is negative 3. Okay, we still need to raise that to the power of 4. Negative 3 to the power of 4 is negative 3 times negative 3 times negative 3 times negative 3, and that's 81 positive. All right, looking at D. D has a exponent that is a decimal. So what we need to do first is raise that to a fraction, or turn that into a fraction. So 7 to the 5 over 2 is what we're looking at here. Again, I can write it two different ways. So I'm going to write both. So 7 to the power of 5 all squared, or 7 squared all to the power of 5. Now, I can't square root 7 and get a nice number. So I'm probably going to choose this method. Now, it's not going to be perfect. Okay, so what we're going to look at is I'm going to show that this is 7 times 7 times 7 times 7 times 7. I could see that 7 times 7 is a perfect square. It's 49. I can do that again here, another 49. And then I'm left with another 7. So I can write this as the square root of 49 times the square root of 49 times the square root of 7. Square root of 49 is 7. Okay, so that's that one. Times another 49 is 7. Times root 7. 7 times 7 is 49. Times root 7. Evaluate each power without using a calculator. So here's where we want to choose what we're doing first. Okay. Let's do A. So A is 1,000 to the 2 over 3. So I can write it in two ways. I can say that we're going to cube root 1,000 squared, or I'm going to cube root 1,000 and then square it. Now, because if I square 1,000, it gets really big already, I'm probably going to choose this method because I know 1,000 is a perfect cube as well. And then it's going to make a smaller number that I can then square without my calculator. So the cube root of 1,000 is 10. 10 times 10 times 10 is 1,000. This is all still squared. So 10 squared is 100. Okay, there's a bunch of these here, so we're just going to choose maybe a couple to do. All right, I'm going to start with C. So to get x by itself, it's currently under a square root. Again, we're doing BEDMAS backwards when we're solving equations. So there's no addition and subtraction in this one, so we're going to go right to multiplication and division. So what is multiplied to x? 16. So to get rid of it, we need to divide both sides by 16. Okay. So I'm left with the square root of x is equal to 180 over 16. Now, to get rid of the square root, we're going to square both sides. But what I want to do first is make this a smaller value. So I'm going to reduce my fraction as much as possible. So I'm going to divide by 4 is what I've figured out is the greatest common factor of these two. So I'm going to end up with 45 over 4. That's the smallest we can go. I'm just going to move over here so I don't run out of room. So the square root of x is equal to 45 over 4. Now, to get rid of my square root, I have to square this side. Therefore, I have to square this entire side, everything that's there. Okay, so x is therefore equal to 45 squared over 4 squared. Remember that the square applies to both the top and the bottom of our fraction. So this comes out to, I had to use my calculator, x is 2,025 over 4. 16. You could put that into your calculator and get a decimal, but this is the exact value, and we want to leave it as an exact value if possible. The other one that I'm going to do is F. I'm just going to start over here. So we have the square root of x cubed minus 5 equals -1. So working with BEDMAS, we have to do addition and subtraction first. What is added or subtracted to our x term? It's that 5. So I'm going to add 5 to both sides. And I get that the square root of x cubed is equal to -1 and positive 5 is 4. So to get rid of our square root, we need to do, there's no multiplication and division, sorry. So we're just going to take care of our exponents. So our exponents here, to get rid of our square we're going to, our square root, we're going to square it. So that leaves us with, oops, no more square root, that's canceled. We're left with x cubed equals 4 squared, which is 16. Now we want to cube root that. Oh, I made a mistake in my notes. Silly me. I said 4 squared was 8, which is not right. Okay. So our next step is to cube root both sides. If we cube root both sides, I'm left with x is equal to the cube root of 16. All right, and we can reduce the cube root of 16. If you show your work, it will be 2 to the cube root of 2. All right, our last example here. The population of a hive of bees is given by the formula P is equal to 710 times the square root of T cubed. Where T must be our population, our time in days, and P is our population of bees. Okay, so find the population after 2 days. What we need to do is we need to put into our equation 2 for time. So P equals 710 times the square root of 2 cubed. So that is 710 times the square root of 8. And if you plug that into your calculator and just round to the nearest whole number, I think we get 2008 bees after 2 days. Okay. After how many days was the population 2,000? So now what we're going to do is we're going to put in 2,000 for our population, 20,000. And now we have to solve for T. So our first step, bed mass backwards, there's no addition and subtraction. We are going to take care of our multiplication and division. So we're going to divide both sides by 710. And it doesn't matter, we're just going to get a decimal value here. So I have said that this is 28.168, and that still equals T cubed all square rooted. So I squared both sides, and I get 793.5 is equal to T cubed. And now to get T by itself, we are going to cube root both sides. So T equals 9.26, so 0.9 days, let's say. All right, the exit task is to write these numbers in exponent form and order from least to greatest without a calculator. I'll give you a hint. When you put them into exponent form, they're all going to be in fractions. Write those fractions with a common denominator and compare those. Okay, it's pretty hard to compare fractions that don't have a common denominator. In the end, you should get the answer of 3 cubed is the least. Then 3 to the 2/3, 3 to the 3/2, 3 cubed all to the power of 5, and then